In this video, we're going to measure the wavelength of light. Now, anyone can do it with a lab full of equipment, but I'm going to show you how to do it with nothing other than stuff that you probably have lying around your home or office. Getting the wavelength of light is a bit of a challenge because it is so tiny, and it may be obvious that because we use light to see things, we can't use it to actually see its own wavelength. So we have to be a little bit sneaky and set up a situation where we can see the effects of light having a wave-like nature, and from that figure out its wavelength. And to do that, we're going to use a diffraction grating. So what's a diffraction grating? Well, it's a small clear section of something like glass or transparent plastic with a whole bunch of black parallel lines on it, or alternately, a whole bunch of clear parallel slits on it. And those lines or slits are very narrow, very fine, so fine that they're some small multiple of the wavelength of light itself. And because they are so close to the wavelength of light, it means we do get some weird interference effects, and that's what we're going to be using. Now, you can certainly go online and buy some diffraction gratings from any number of online retailers, from anywhere $20 to probably over $100, and those will be very nicely built, but it's really not very satisfying if you have to go out and buy something fancy to do an experiment like this. It would be much neater if we could make a diffraction grating at home, and I was wondering if we could use something like a common laser printer to do just that. And I actually did some looking in some of the online physics forums, and a few people had discussed it, but I couldn't find anywhere where someone had actually tried it. So I did. And to put things in context, I'm going to use a 20-year-old HP LaserJet printer. And at that time, common LaserJet printers, including this one, had a resolution of 600 dpi, that's 600 dots per inch, meaning in theory we could draw 600 pixels per inch on our piece of paper. So all we need to do is make a picture of a grating with alternating 1 pixel wide lines of black and then white, and repeat that over a certain area and send it to the printer. Not quite that easy, because it turns out if you're using an operating system like Windows or any of the other common ones, you have a printer driver in between you and the printer. And on top of that, you're going to be probably using a program like Photoshop or some sort of paint program. And by the time all of that's done, if you try and draw a whole bunch of very narrow lines alternating at 600 dpi, it's very hard to be sure whether they're going to get lined up with the pixels on the laser printer itself after all that processing. And if they're not, you're going to get some sort of weird gray mixture of those lines and not a very satisfactory result. So what I had to do was do a bunch of things to get around all of that mess. And the first thing I did was write a little Java program that would connect directly to the networked printer port at port 9100 of the laser printer, meaning it was not going through any of the Windows printer drivers at all, but simply talking directly to the printer. And that's not too hard a thing to do if you know how, but the harder thing was now having to figure out what to send the printer. And HP printers use a printer language called HPPCL, which is how all the drivers actually talk to the printer. And it does have commands for drawing images, very primitive images that are simply pixels that are on or off, but you can draw them at 600 dpi in the case of my printer. And of course, those pixels are the exact pixels that the printer eventually prints out to the paper, or in our case, a transparency sheet. Well, after a whole bunch of frustrating experimentation, I was able to do it, and I created a raster image in HPPCL of a whole bunch of single pixel wide black lines beside a whole bunch of single pixel wide white lines alternating, and I sent that to the printer, and here's what I got: a nice black square. Well, what's going on here? It turns out that the actual particles in the toner are so big that when you draw a 1 pixel wide black line, the particles in the toner actually spill over into the white space left or right of that line. And they spill over so much that if you do what I did, you essentially get no white space left. It pretty much clogs those thin white lines that I so nicely created. Well, okay, 600 dpi doesn't work. It's pretty easy to tell the printer, just print that at 300 dpi. And sure enough, we now get a nice pattern of somewhat thicker black lines than white lines, but we do have a diffraction grating, but not as fine as I'd hoped, and I want it to be as fine as possible. So, one more attempt, and that was to say, what happens if I draw 2 white lines next to each other, then 1 black line, and then 2 more white lines, and so forth. So the white lines were essentially twice as thick as the black line. Well, do that and print it at 600 dpi, and here's what I get. Yes, it is probably about as fine a diffraction grating as I can draw with this printer, and if we look at it under the microscope, it's not too bad in terms of size of those white slits, which is what's really important to us. You'll notice that the whole thing is pretty crude, but you'll be surprised how well that'll actually work when we try it. So for the laser, we'll use an old IR laser thermometer that I had lying around, and I'll clamp it into a Black & Decker Workmate and point it towards the wall of my workshop and turn it on by using some electrical tape to keep the trigger depressed. And surprise, surprise, we get a nice red dot on the wall. The interesting part is when I take the diffraction grating that we printed and position it so that it is between the laser and the wall, and we suddenly get a nice series of red dots instead of just the single dot we originally had. That shows us that the diffraction grating has taken the light and, maybe quite surprisingly, split it off into a bunch of beams, each going out at a slight angle to the original. And it turns out that the angle that they're split off is directly related to the spacing of the lines in our diffraction grating and the wavelength of the light. At this point, what I'd like to do is take some measurements from this, which we'll use later to actually determine the wavelength of light. So what I did before I made the video is I set things up so that the laser is 2 meters away from the wall. So all we really have to do is measure the spacing between the dots. And if I take a tape measure and put it near the dots, it looks like the dots are about, shall we say, 10 millimeters apart or so. Maybe what we'll do is try and measure the distance between 2 of the dots to get something perhaps a little bit more accurate. And if I look at it, at least from here, it looks to be maybe 21 millimeters or something like that. So what that probably means is a spacing of about 10.5 millimeters between the dots is the best estimate we can get using this very crude setup. Okay, so I said I would show you why we get that splitting of light into multiple beams, and that's what we're going to do right now. We'll start off with a very simple setup where we have a diffraction grating, this black line, with a single small hole in it and a red laser pumping out nice parallel waves until they hit the diffraction grating, and the diffraction grating has just a tiny slit, and when the light hits that slit, well, when it gets to the other end, it comes out and forms nice circular waves, just like we would get when we throw a pebble in a pond. And in this diagram, I'd like to consider the red lines to be the crests of those waves, and the distance between the red lines or those crests is the wavelength, which we'll denote as lambda. But of course, one hole doesn't really represent our diffraction grating very well, so what we'll do is consider the case of two holes or two slits. And I can say slits because we're looking at this from above, looking down, so this is the edge of that diffraction grating. Now we have two slits, 1, 2. The second slit is shown in orange, but it's not like it changes the wavelength of light from red to orange or anything like that. I've just used orange to make it clear which ones of these waves come from which slit. And just like the first slit, we have nice circular waves coming out of the second slit. And what's really interesting is where the crests of those waves hit or intersect. Well, they add together, and if the crests of these waves are the same height where they overlap, they add, and now we have a little point of a wave, a crest of a wave that is in fact twice the height of the original waves. And if we consider the white areas between the crests as the trough or the valley of those waves, well, if we have a orange crest hitting a red valley, they add together, and when you add them together, you get nothing. They cancel out. So that is destructive interference. This is constructive interference. And what you can see here is there's 1, 2, 3 points where we clearly have constructive interference in a line. And if you imagine these waves are moving out in their semicircles, well, what we'll get is in fact a line of nice, bright, constructive interference. And what that is, indeed, is a nice straight beam of light that's going out straight ahead, essentially the continuation of our original laser beam. In other words, that original dot that we saw on our screen, the dot in the center when we had multiple dots. But it's kind of unclear what happens at angles, and even for that matter, how this center interference ends up really in a continuation of these parallel waves. So to make it a little bit clearer, what I'm going to do is replace this diagram with one that only shows pie-shaped sections of these circular waves so we can get a clearer idea of what's going on. Okay, so now with the somewhat reduced amount of waves, what we can sort of see is these waves here sort of continue on a straight line, and you can imagine if we had another hole in our diffraction grating here, we'd have another wave that sort of continues this, and same thing on this side, and same thing for these waves, again something like that. And what you would expect to get is a nice straight series of parallel waves coming out, essentially the continuation of our original laser beam down here, just continuing straight up to our original point. And it is worth pointing out that indeed, if we do have a whole bunch of these holes or slits in our diffraction grating on either side, many of them tens, preferably hundreds or thousands, it turns out if you work through all the math, you indeed get nice, straight, parallel waves, and all the sort of wobbliness disappears. But we won't bother with that math in this video. So that's all very nice, but what about the wave that started going off on a direction like that? Well, once again, what we'll do is use some pie-shaped sections of wave, but we'll direct them a bit like that, so once again we can see what's going on. The waves coming out of our two holes, just showing the parts that we're interested in. And if we take our transparency sheet and try and line up its nice parallel wave crests to the semicircular ones, what you can see is over here they match up quite nicely. And once again, if we had a whole bunch of holes, it would all work out so that these slightly wobbly combinations of wave fronts indeed become nice and parallel. The interesting thing is, if we look down here and we follow this crest here from this slit in the diffraction grating over to the next, well, this distance here is 1 wavelength. And so that's the key to how we're going to figure out what the wavelength of light is. We know what this angle is, and we know what this distance is. It's the distance between the slits and the diffraction grating. And so we should be able to calculate the wavelength over here. We can take this one step further, try an even bigger angle. Once again, we'll try and line up our transparency sheet nicely with the semicircular wavefronts that we're dealing with. That's about it here. And sure enough, watch what happens when we follow the hopefully parallel crest that goes through this diffraction grating hole up here. Well, how far is it from the next diffraction grating hole? It's 1, 2 wavelengths. So that's the pattern. Each one of the off-center dots of light that we see on the screen corresponds to an increasing shift of these parallel waves from the next over diffraction grating hole by 1 wavelength. So if you have a background in antennas and think you've seen this somewhere before, well, this is indeed a phased array antenna. Each of the holes or slits in the diffraction grating corresponds to an antenna, and when it's angled like that, it's effectively equivalent to beam steering. If you have a mathematical background, the slits in the diffraction grating correspond to a periodic function, and the bright points that we see on the observation screen are the magnitude squared of the Fourier transform of that periodic function. Now you've seen why we get that pattern of dots, or most obviously why we get the dot immediately to the left and right of the center dot when we insert the diffraction grating. But using what we've done, let's take a look at now how we can actually calculate the wavelength of light based on the dot spacing and the distance from the diffraction grating. Over here is our screen, or the wall that I use to see the dots of light. And down here is the diffraction grating with its various holes. And what we'll do is take an interest in this hole and say we have a nice straight ray of light ending up here, and this is of course our bright center spot, the spot that we got when we didn't have a diffraction grating at all. Now on our screen we also have some smaller spots, some dimmer spots I should say, on each side, and one over here. And we'll take an interest in the first one, and once again we'll draw the ray or beam of light corresponding to the first off-center dot like this. And we might as well put in a few things that we know. We know the distance between these two dots, which we'll call x, and which we decided was 10.5 millimeters when we measured it. We'll also make a note of what this distance is, and really this distance or this distance is actually pretty much the same because this angle is really very small, so this picture is highly exaggerated. But anyway, what we'll do is we'll say this distance over here is L, and it is 2 meters to 1,000 millimeters. Well, that's very nice. What we should really do now is see if we can somehow use these angles to figure out the wavelength. And if we were to take this beam here and make a beam at right angles to it, or make a line, I should say, at right angles to it, we'll get something like that. And maybe what I'll do is do that to denote these things are at right angles. We should also point out that this angle over here is of importance. It's called theta. And because this is at right angles and this is at right angles, this angle over here is also theta. Okay. Well, what we're really interested in is this distance over here. And I'll try and draw a line parallel to that one. This dotted line corresponds to the crest of the wave that's coming through this slit and is one wavelength away from the next slit. So that distance is wavelength, or lambda. And there's one more thing we need to know, and luckily we do know it, and that is the distance between our slits in the diffraction grating, and that distance is 127 micrometers. And we'll call it D. Okay. So it should be pretty easy now to figure out what that is, because these triangles are similar triangles. So we can write down a nice simple equation. The short side over the long side, lambda over D, is equal to the short side, x, over the long side, L, of the big triangle. And we're, of course, interested in lambda, so we'll multiply both sides by D. Lambda equals x times D over L. And we can now just fill in the values of all of these things. I'll write it on the other side so there's some space. Lambda equals x. Well, x is 10.5 millimeters times D. D is 127 micrometers, or 0.127 millimeters, all divided by L. And L is 2,000 millimeters. And if we put that all into a calculator, what we get is 0.000667 millimeters. And if we move the decimal point 6 spaces, what we get is lambda is equal to 667 nanometers. And You know, that's really way beyond the accuracy that the crudeness of this experiment gives us. So we'll just get rid of the last position here and say lambda equals 670 nanometers. So there you have it, 670 nanometers, not bad at all compared to the 630 to 670 nanometer specification for the red laser on that IR thermometer. If we'd bought a fancy diffraction grating with a finer pattern, the dots on the wall would have been further apart and would have been easier to measure, and we probably would have gotten a more accurate result. But I'm quite thrilled with how well we did, given how crude the homemade diffraction grating was. Now, if you found that interesting, a few months ago I did a similar video on how to measure the speed of light, and there should be a big rectangle up there that will lead you to it if you click on it. I should also point out in both videos we use lasers, and a word of caution, never ever let a laser beam get in your eye or anybody else's, or even a reflection from something like the piece of plastic we use to make the diffraction grating. It can lead to severe eye damage, so please be careful as always. Well, that brings this video to an end. I hope you enjoyed it, and see you next time.